So we start with this today's class, and the objective of this particular part of the work is to look at the advanced aluminum alloys, particularly those with high strength. So when we look at high strength alloys, most of the alloys with high strength aluminum alloys are basically nothing but those nanocrystalline alloys or nano-quasicrystalline alloys or amorphous alloys or composites of all these. So let us try to look at some of the work that has happened in the world so far on these kind of alloys. So if you look at the first transparency, this is basically nothing but how amorphization occurs in a simple binary system. Though usually in a binary system we all know that the glass forming ability is very poor, particularly aluminum based binaries. It's very difficult to make glass, but there are a few systems where people could successfully make it. This is one of those systems, aluminum titanium, where you can see with increasing time of ball milling you have destruction of the crystalline structure and then finally the development of the amorphous phase beyond a certain strain. And if you can look at the range of glass forming compositions, what is called the glass forming range, GFR people usually call it, that means the composition range over which one can get a glass, it is very wide in this system, 25 to 90% of titanium. Whereas if you look at the same system, aluminum titanium system, by rapid solidification processing, if anyone of you have looked at this phase diagram of aluminum titanium is basically peritectics. There are a number of peritectics in aluminum titanium phase diagram, and there are no eutectics, and because of which you know that if a system does not have eutectics, it is very difficult to form a glass. We know, we have considered all the various criteria of glass formation, and we know by now that it is only deep eutectics which are amenable for glass formation when a liquid is being cooled. So if you want to have good glass forming ability, you need to have deep eutectics, whereas if you don't have eutectics at all, then it is very difficult to form a glass. I would not say it is impossible, because we know, but because of the kinetic constraints, if one can cool it very rapidly and somehow suppress the formation of the crystal, he can always get a glass. But those cooling rates are very high and difficult to be achieved in normal practical circumstances. So as a result, this system is one example where you can easily get a glass by high energy ball milling when compared to rapid solidification, and shows the kind of an advantage that we have by this solid state processing route when compared to the liquid state processing route such as rapid solidification. This is the binary. As I told you before, when you add more number of elements, the glass formation becomes easier. Aluminum is not an exception. So in aluminum systems also, if you can add a ternary element, the glass formation becomes very easy. This gives you an idea of in aluminum transition metal systems, how the glass formation occurs, in what kind of systems you can easily get a glass, in what kind of systems it is more difficult to get a glass. If you look at any of these aluminum transition metal systems such as aluminum iron, aluminum cobalt, or aluminum nickel, or aluminum copper, if you add some zirconium or titanium or hafnium, these are the three which can easily give you a glass, because these are the elements which are much bigger atoms when compared to aluminum, and that gives you very easy glass formation. As I told you before, you always, for a good glass form ability, you need a big atom, a small atom, and an intermediate atom. Aluminum is basically that kind of an atom with about 1.47 or so as the atomic size, and copper, nickel, these are all about 1.28, 1.27 as the atomic size in angstroms, and zirconium is much bigger. So as a result, if you look at these kind of systems, it is very easy to form the glass. And there are rare earth systems, aluminum based rare earth systems, where glass formation is very easy. Most of the aluminum rare earth systems, glass formation is very easy, but the composition ranges are very narrow. If you look at this system, there are number of binary aluminum rare earth systems shown here: aluminum yttrium, aluminum lanthanum, aluminum cerium, aluminum neodymium, aluminum samarium, gadolinium, and so on. And if you look at all of them, in all the cases you can get a glass, and this box tells you the composition range in which you can get a glass. It is usually in the range of around 10. which is close to the actual deep eutectic compositions, the eutectic compositions. I won't say deep eutectics, there are not really very deep eutectics in these systems. So these compositions are close to the eutectic compositions, and this also shows you that there are certain intermetallic compositions, intermetallic compound forming compositions which are shown here. So the glass formation occurs away from these intermetallic forming compositions. So and this second figure gives you in a wider composition range slightly magnified view of this to show you what is the glass forming range in all these systems. You can see aluminum samarium shows the almost the highest glass forming range when compared to all of them. So but in all cases you can get glass, and one if you add some ternary elements again into aluminum rare earths, then you can enhance the glass forming ability, which we have talked about it before also. So you can see this is aluminum, yttrium, various metals, transition metals, for example iron, copper, cobalt, nickel. So this domain tells you what is called the glass forming domain. On one side yttrium, on the other side the metal percentage is plotted. So you can see this particular domain gives you what is the glass forming range, and for various yttrium, lanthanum, cerium type of rare earths, if you put various transition metals, how the glass forming domain can be expanded can be seen in this kind of a figure. So one can really expand. You can see that in the binary, if you don't put any ternary element, the binary, the glass forming range is very small. You can see it is around 10%, maybe 8 to 12. In most of the cases it is something like around 8 to 12 or 10 to 12 or 10 to 11. This is the small range, whereas if you put certain ternary element, it can be made much wider, as you can see here, or you can see in case of cobalt or copper or nickel is much more wider. So like that one can widen the glass forming ability range. The question is, why do you want to do that? You want to do that because there are a number of advantages that you get in these amorphous alloys. The strengths that you can achieve are very high. You can see in some of these aluminum transition metal rare earth systems, it is shown here, particularly aluminum nickel rare earth metals with various rare earths, yttrium, lanthanum, cerium, and for different compositions you can see the fracture strength is of the order of almost 1 gigapascal, which is much higher than any of the commercial aluminum alloys. I will also show you some more comparisons with the commercial alloys, where you can see very easily the difference between these alloys. But one problem is, you can see the ductility is still not very good. About 1.5%, 1.6%, 1 to about 2% is the ductility. So that's one of the I would say the drawbacks. So one cannot use them really in tensile conditions. Wherever you need a good compressive strength, probably you can easily use it, but the uniaxial elongation is not very high. You can also see here another system, aluminum nickel cerium, aluminum nickel yttrium, the glass forming ranges, yttrium and nickel shown here, and here we also show which are the compositions where you can possibly get a ductile amorphous. It is not that always amorphous phase is very brittle. If you can control the composition in such a way, particularly keep the rare earth element to very low. If you add large amount of rare earths, it becomes very brittle, and similarly if you add a large amount of transition metal also, it becomes brittle. For example, you can see all these open circles, these are all brittle amorphous materials, whereas wherever you see the thick circles shown here, these are all ductile amorphous. So you can see if you go to large amount of transition metals, you get a brittle amorphous phase. Otherwise one can vary the composition and can still get ductile amorphous. And here is an example that you have really a ductile amorphous, that you can make a wire out of it, aluminum nickel cerium amorphous wire, and can bend it 180 degrees without really breaking it. So most of the amorphous alloys, if you try to bend like that, they immediately break. So one can have good bending ductility, and this is in case of wire, and this is in case of melt spun ribbons, the DSC curves, to show that basically the nature is the same whether you make a wire or you make a melt spun ribbon. So more or less you get similar DSC plots, and you can easily show that some amount of ductility is there, and there is a lot of shearing which occurs. You can see all shearing in these wires. And you can also take these amorphous alloys made by either mild spinning or by ball milling and extrude them, make into rods, and look at their mechanical properties. And if you compare the mechanical properties here with a conventional aluminum copper magnesium alloy, you can see these aluminum nickel yttrium alloys have much higher strengths of the order of almost 1.5 gigapascals. Though this is compressive strength, you have to remember, we are talking of compressive strength and not really tensile strength. So you can get very high strengths, but aluminum nickel yttrium alloys are not really good for ductility. But if you replace yttrium with cerium, what you can see here, aluminum nickel cerium gives you sufficient amount of ductility. So you have to control the composition in such a way that one can have a good combination of strength and ductility. Similarly, you can also look at high temperature strength. A conventional aluminum alloy, high strength alloy, loses its strength very rapidly, more or less, and you cannot really use them beyond about 300 degrees centigrade, I told you, and this is shown in terms of Kelvin. So almost around 573 Kelvin. Beyond that you lose the strength very rapidly, whereas these extruded aluminum nickel yttrium amorphous alloys show you much higher strength even at higher temperatures. So this is one of the advantages of going for such so to say exotic alloys, which are metastable, though definitely they are all metastable alloys. So we know that at very high temperatures they tend to crystallize, but we are going to talk about those things also, that one can crystallize them and get nanocrystals out of it and then use them for our advantage. So we will go to those alloys also a little later, and that is where you come across what are the various possibilities. We talked about it in the last class, that one can have various combinations when we are talking of nanocomposites. You can have an amorphous with alpha aluminum nanoparticles, you can have aluminum with intermetallic nanoparticles, you can have amorphous and quasicrystalline intermetallic particles, or you can have aluminum grains with quasicrystalline nanoparticles, or you can have other combinations also. So various varieties of combinations are possible, and one can really realize all these things by choosing a proper composition and proper temperature and time of heat treatment, so that you can end up in all these kinds of microstructures and look at their mechanical properties. We are going to look at some of such microstructures and their mechanical properties. This is one such system, aluminum nickel cerium iron. So take aluminum nickel cerium, put a small amount of iron in it. You have seen earlier, aluminum nickel cerium is basically an amorphous alloy. If you put a small amount of iron into it, it leads to the formation of easy crystallization and gives you nanocrystalline aluminum particles embedded in an amorphous matrix. And that shows you that if you increase the volume fraction of those embedded nanoparticles of aluminum, that the strength increases, the hardness increases, Young's modulus increases, and one can achieve very good strength levels here, and one can talk in terms of about almost 1.5 gigapascals fracture strength in all these alloys. That one can vary the volume fraction, and you can see that there is a volume fraction beyond which, if you go to much higher levels, you are not going to get any additional advantage, basically because you need these nanoparticles to be separated by an amorphous matrix. The moment you start seeing that these nanoparticles start joining with each other, then you will see the crack propagation occurs at the grain boundaries of these nanoparticles. So you need to have always an amorphous kind of a region which is engulfing the whole nanoparticles. So you need to have a matrix of amorphous, and then in which these nanoparticles are embedded. And similarly, if you have a look at the high temperature strength, you can see you can also achieve much higher strengths at even higher temperature, but there is a temperature beyond which they show some kind of brittle nature. So one has to consider this aspect also. This is basically because of the precipitation of crystalline phases at high temperatures, which make them brittle, because most of these crystalline phases are intermetallics, brittle intermetallics. So because of which high temperature you lose the ductility to a large extent. One can also make bulk nanocrystalline alloys. This is one such example of aluminum nickel mish metal type of alloys. Mish metal, have you heard of what is a mish metal? Mish metal is basically an alloy consisting of rare earths. For example, if you have an alloy of lanthanum, samarium and cerium, alloy of all these, because whenever you are trying to extract these rare earths, most of these rare earths in the earth's crust, they are all together. So when we try to extract, individual extraction of these rare earth elements is very difficult. So most of the time what people do is they generate a kind of an alloy during the extraction process, which consists of a combination of all these rare earths, and people call them as mish metal. And wherever you are not particularly looking at any one of the rare earth element, one can use this kind of a mish metal, which is a combination of various rare earths. You have lanthanum, about 40% of lanthanum is there, about 30% of cerium is there, and some amount of samarium and things like that, some amount of gadolinium. So if you take aluminum nickel mish metal type of alloy, and then look at the creep properties or stress rupture strength as a function of temperature, you can see you get much higher strength when compared to conventional aluminum 7075. What is the 7075 alloy? Aluminum zinc magnesium alloy. Very good. So if you compare with a standard aluminum zinc magnesium alloy, you get a much higher strength in these alloys at any temperature of your consideration. So you can even talk in terms of up to around 600 Kelvin, and you get much higher strength. And similarly, look at the fatigue strength of this alloy and compare with any of the conventional alloys. All the conventional alloys fall here, and this aluminum mish metal alloy is much higher. So it has a good combination of tensile strength of almost around 1 gigapascal and a good amount of fatigue strength. So these have a good combination of both strength and high temperature properties. So you can have a good creep strength, creep resistance and fatigue resistance, and in addition a good tensile strength. So that way these kind of bulk nanocrystalline alloys produced by the crystallization of the amorphous alloy. As I told you, there are two ways of doing this. One way, we talked about it in the last class, one way is to get a glass by rapidly cooling the alloy, or by making going through the process of mechanical alloying or high energy ball milling, and once you get the amorphous alloy, then crystallize it at temperatures and timings which can give you these nanocrystals. That is one possibility. Other possibility is that use a cooling rate during rapid solidification in such a way that you get a combination of amorphous plus the aluminum. As I showed you in the last class, if you look at the TTT diagram, if this is aluminum and this is intermetallics basically, and you have a TG here, if you try to cool it very rapidly, you get a glass. If you try to cool it at an intermediate rate, you get an amorphous, and whatever is left out will give you a glass. And if you cool it very slowly, you get a crystalline aluminum plus some intermetallic compounds, whatever crystalline intermetallic compounds. So similarly, you can see intermetallics always are below and to the right in the TTT diagram. Why is that? They are to the right and below in the TTT diagram. What does that mean in the TTT diagram? We have gone through all this. Why? Because the nucleation of these intermetallics is more difficult when compared to nucleation of aluminum. You can see aluminum is simple FCC, so it can easily nucleate and grow, whereas intermetallics are mostly ordered and also have certain stoichiometry. So, because of that, the nucleation and growth of such intermetallics is more difficult. As a result, you always need more time, the incubation period is longer, and at the same time you need a higher undercooling. If you do not give higher undercooling, you can't get, you need a higher driving force. Unless you provide a large driving force, you cannot nucleate. So, that is why you will see this kind of intermetallic compounds are there. So, if you still cool it very slowly, you get a combination of aluminum plus intermetallic compounds, but otherwise you can get. And in case you have a quasicrystals in a system having a Frank-Caspar phases, you will have, let us say, a quasicrystals somewhere here or maybe somewhere here, depending on the type of system, so that you can have a combination of amorphous plus quasicrystal or amorphous plus aluminum plus quasicrystal. All kind of combinations are possible. Okay. So, this is the bulk nanocrystalline alloys, and one can show in some of these nanocrystalline alloys that they can even be superplastic. This is one aluminum nickel mischmetal alloy, which is you can see the undeformed sample, and after deformation you can almost have about 480% deformation. So, you can just elongate it by almost 480%, but provided you use a proper temperature. This is one important point that you should also know, that have you ever heard of what are called deformation maps? You have all gone through deformation course, I suppose. Every material can be deformed in a easy fashion if you choose the proper strain rate and the temperature. Each metal, for example, if you take a metal, deform it at very high strain rates, it becomes brittle, it breaks very easily. Similarly, if you take the material and deform it at a very low temperature, again it behaves in a brittle fashion. So, there is a particular domain, a particular window of temperature and strain rate. If you plot a domain of temperature and strain rate, you can identify a domain where dynamic recrystallization easily occurs and the deformation becomes very easy. And such domains, these are called have been identified by a number of people, and the person who started this is a person by name Rishi Raj. These are called Rishi Raj maps, and a number of people have worked on this, particularly in IISc Bangalore in India, Professor Y.V.R.K. Prasad, if some of you have heard. So, he has done a lot of work on various alloys, titanium based alloys, super alloys, aluminum based alloys, aluminum lithium alloys. In all these alloys people have worked and identified what kind of domain is this. So, because it is very important when you want to commercially make alloys with various shapes, you need to identify this temperature and time, particularly when you are developing newer alloys such as, let us say, nickel based super alloys or alloys like that. Unless you really identify this domain, it becomes very difficult for you to process it over a very large amount of deformations. And particularly in case of bulk nanocrystalline alloys, because you have a fine crystal size, some of these alloys can behave in a superplastic manner, and that is where you can see here at about 873 Kelvin. So, that means about 600 degrees centigrade. If this alloy is deformed at a strain rate of 1 per second, one can achieve almost 480%, and these have been also deformed by superplastic manner, forged into various shapes, and a number of shapes have been made in alloys like this without much problem. Let us now come to the aluminum based quasicrystalline and nano-quasicrystalline alloys. As I told you before, quasicrystalline phases can be obtained in a number of systems, and aluminum based system is the starting point. What was the first alloy where people have observed a quasicrystalline phase? Do you remember?
Sir, aluminum silicon.
What was the first alloy where aluminum manganese? Aluminum 14% manganese is the first alloy where people have observed in 1984. Don Shetman the quasicrystalline phase. So after that, a number of aluminum alloys people have observed quasicrystalline phase, and now people do not want to use this kind of quasicrystalline phase as a single quasicrystalline phase. If it can be obtained in a nano-quasicrystalline fashion, one can have much better properties. So people are looking at such nano-quasicrystalline phases, and these nano-quasicrystalline phases can be obtained in a number of configurations, a number of microstructures. For example, you can have an aluminum matrix in which you can have a nano-quasicrystalline particles. You can also have some grain boundary precipitation of quasicrystalline phase in an aluminum alloy. You can also have in a quasicrystalline alloy in which aluminum nanoparticles have been precipitated by choosing a proper composition. So in all such cases, one can achieve very good mechanical properties, and we will try to see some of those mechanical properties. And these diffraction patterns show you in some of these alloys that these are quasicrystalline in nature. For example, the 10-fold pattern that you can see, and the 3-fold pattern with a quasi-periodic arrangement of atoms, arrangement of diffraction spots. I should not say atoms, these are diffraction spots, and one can get an idea that these are basically quasicrystalline. And look at some of these systems. This is aluminum manganese cerium. We talked about earlier aluminum nickel cerium, where you can get a completely single phase amorphous alloy, whereas if you replace that nickel with manganese, if you take a aluminum manganese cerium, we already know that in aluminum manganese you get a quasicrystal, but if you add cerium to it, you can get a nano quasicrystalline phase and a bulk nano quasicrystalline alloy, and this gives you an idea of the composition ranges of cerium and manganese to get various phases. For example, here if you have a high amount of cerium and manganese, you get completely amorphous phase. That means beyond this dotted line you get amorphous phase. You can have a quasicrystal plus amorphous combination. You can have a FCC aluminum plus quasicrystal combination, or you can have a FCC aluminum plus amorphous combination by choosing the proper composition. So depending on the choice of the composition, one can achieve various microstructures like this, and the strength levels are also shown here. For example, that you can have strengths of the order of around 1.3 gigapascals, 1300 megapascals, and you can also see here that some of the compositions are brittle, some of the compositions are ductile, and particularly those compositions with low amount of manganese and cerium, they are all ductile, and if you add more amount of manganese and more amount of cerium, they become very brittle. So one can control the ductile brittle nature of these alloys also by choosing the proper composition. And this is another example where aluminum nickel mish metal with some zirconium or aluminum chromium cerium with cobalt, various nano quasicrystalline alloys. And if you try to compare with conventional alloys, all these circles are all conventional aluminum alloys. Conventional aluminum alloys, if you look at their strength elongation combinations, they are all very low strength alloys. And if you can make these the nano icosahedral alloys, you can achieve much higher strength. Okay, so you can have a good combination of strength and ductility by choosing the proper compositions in these alloys. And this is another example of bulk nano quasicrystalline alloys where aluminum iron chromium titanium. This is entirely a different route. There is no rare earths here. We don't use any rare earths, only aluminum and transition metals. You can put iron, chromium, titanium. Some of these elements have a tendency to give you nano quasicrystalline phase. So if you can properly choose the composition and make an alloy like that, you can make these alloys with very high strengths. For example, conventional aluminum alloys 20 series has strength levels like this as a function of temperature, and usual Air Force limit, Air Force goals are also shown here. Particularly the defense aircrafts want to have very high strengths at high temperatures. Why do they want high strength at high temperature? Efficiency becomes higher. Anything else? Raise? Creep, not that.
The microstructure aluminum alloys assess the fuel, the weight comes down.
But during the actual application, like due to the supersonic
speeds,
speed,
particularly that's the aspect. So most of the Air Force aircrafts nowadays, people want to go to higher and higher speeds. If you want to go to high, because you want to go and hit the target before anybody notices you, isn't it? So for that you need to really go at high speeds, Mach 2, Mach 3. So these are the kind of speeds everybody wants to achieve. And if you want to go to high speeds, you always have a friction from the air, surrounding air, okay, and the friction results in a lot of temperature rise. So you need to use alloys which have high strength at high temperatures. So as a result, one puts a goal like this, and there are a number of these aluminum, iron, chromium, titanium alloys which can achieve all those goals, and people are still working on this. And some of the achieved goals, for example, aluminum, vanadium, iron, I am going to show more results of that, and aluminum vanadium iron has much higher strength than what is the objective that is set as the goal. So people have been able to achieve these goals of very high strength at high temperatures by making these nano-quasicrystalline alloys. One can also make these by the ball milling route, and these are some of the examples of that. So for example, if you take aluminum, iron, chromium, titanium alloy, some particular composition, and go through by mechanical alloying route, what you ultimately end up is a solid solution, because all these alloying elements will dissolve into aluminum when you start taking these elemental blends. That means you take pure metals, mix them together, put it in a ball mill and continue ball milling. After some time, all these alloying elements dissolve. And then if you look at, this is for various alloys with different compositions. In all cases, you basically get a solid solution, and if you take the solid solution and then crystallize it, you can get the formation of icosahedral phase, but one has to control the temperature, otherwise you also end up in some crystalline phases like this. So one can control, if one can have a proper control on the temperature and time, one can only get the nano-quasicrystalline phase and generate the strength levels that we have talked just a while ago. And one can also make bulk nano-quasicrystalline alloys in simple systems such as aluminum, copper, iron. This is a standard composition. A lot of people have worked on it. For example, aluminum, copper, iron is known to be a stable quasicrystalline composition. Stable, what do you mean by that? Stable means you take a liquid, cool it slowly. By a normal casting process, you can get a quasicrystal. You don't need to do any fast cooling. Just take like any aluminum, normal aluminum, you melt it and cast it. So similarly, you melt this aluminum, copper, iron alloy. And the composition is 65, 20, 15. 65 aluminum, 20 copper, 15 iron. This particular composition is called the stable quasicrystalline composition. So if you can choose that composition and then melt aluminum, that alloy, all the three elements together, and then if you can cool it slowly, you can generate a quasicrystalline alloy. But the problem is, if you get a alloy by that casting route, the quasicrystals that you are going to get is going to have a large grains, and that is not going to give you very good properties. So if you can generate them in a nanocrystalline form, as you can see here, one can have much higher properties. So that's the advantage of going to either rapid solidification or ball milling routes like that, that you can generate these same quasicrystalline phases in a nano form and then achieve much better mechanical properties. And one can also identify which are the best compositions for making this. For example, as a function of E by A ratio, if you look at it, there is a certain E by A ratio of about 2 to 2.1, where you get the stable quasicrystalline phase with 100% volume fraction of the I phase. Otherwise, if you are either on both the sides, you get only a small amount of icosahedral phase, a nano-quasicrystalline phase, but not 100%. If one wants to get bulk nanocrystalline alloy with 100% icosahedral phase, one has to choose the composition properly. This is very crucial. So, and for choosing the composition, what is crucial parameter is not really the composition, but it is the E by A ratio, because as we have seen earlier also, that the quasicrystalline phases are basically what are called the Hume-Rothery phases. Like if we know in case of copper zinc alloys, you get a beta brass at when the E/A ratio is 1.5. Like that, you get various phases at various E/A ratios. So quasicrystals also form at certain E/A ratio. They don't form at certain compositions. They have fixed E/A ratios. So similarly, you can see this particular aluminum, copper, iron also. If you can fix the E/A ratio properly, you can get a 100% quasicrystal. And some other interesting properties other than mechanical properties of these nano-quasicrystalline phases is their what is called semiconducting nature. Usually most of the crystals have a metallic nature. For example, if I take aluminum, copper, iron, all the three elements together make an alloy, and this alloy I look at its electrical resistivity as a function of temperature. You see that the electrical resistivity increases with increasing temperature. This is the bottom curve that you can see here. But the moment you make it into a quasicrystalline phase, then immediately you see a negative temperature coefficient of electrical resistivity, which indicates that from a metallic nature we are converting into a semiconducting nature. People are trying to exploit this nature of these nano-quasicrystals also. A lot of work is going on these alloys. But as metallurgists, we are more concerned about the mechanical properties, so we will discuss a little more on those. One more alloy system is aluminum iron vanadium, where you can again generate these nano quasicrystalline phases either in an amorphous matrix or in an aluminum matrix. For example, you can see here if you take a composition such as aluminum 94, vanadium 4 and iron 2, just a small amount of vanadium and iron, only 6% of it, okay, mostly it is aluminum. If you take that and heat it, cool it by melt spinning at different cooling rates, 20 meters per second, 30 meters per second. These meters per second basically means the linear velocity of the melt spinning wheel, and we already know that this velocity is related to the cooling rate. The higher the velocity, the higher the cooling rate. So as a result, you can see that at low velocity what you end up is aluminum peaks plus a quasicrystalline peak. So you get a mixture of aluminum plus nano quasicrystal here if you use a low cooling rate. If you use a high cooling rate, you have amorphous, you see a broad peak there, and aluminum. So it is very difficult to avoid aluminum here, because as you can see this particular alloy is such that probably the aluminum, if I look at this, the aluminum, if it is like this, the TT curve for the aluminum. So whatever cooling rate you adopt, you will always hit this aluminum, isn't it? And if you choose a cooling rate in such a way that you get a quasicrystalline phase, you will end up in aluminum plus quasicrystal. If you use a cooling rate where you don't touch the quasicrystalline phase and go up to the TG, you will get some aluminum, and the remaining liquid transforms into an amorphous phase, and that is what exactly you see here. If you go to high cooling rates, that you will end up in aluminum plus amorphous. If you use a slow cooling rate, you will end up in aluminum plus the quasicrystal. If you still use much slower cooling rate like conventional cooling rates, you may not end up in any quasicrystal, but ultimately only aluminum plus some intermetallic compounds which are corresponding to that particular phase diagram, equilibrium phase diagram. So that is what ultimately you get. So whereas under non-equilibrium processing, you end up in these novel microstructures such as either a combination of nanocrystalline aluminum plus amorphous or nanocrystalline aluminum plus quasicrystalline. And if you look at the DSC, if you go to higher cooling rates, you get two peaks basically. The first peak is where amorphous phase becomes quasicrystal, and the second peak where the quasicrystal becomes crystal. So you have this kind of, in this at low cooling rate you get only one peak where the quasicrystal which is there will give you crystals. So because there is no amorphous phase there. So like that one can see, depending on the cooling rate, one can also get an idea from the DSC what kind of phases are there. And look at the TEM images. You can see when you have low cooling rates, you have spherical particles of quasicrystal in a aluminum matrix. You have an aluminum matrix with a very fine particles ranging from almost about 5 nanometers, very fine particles, up to almost about 70-80 nanometers. And these are all quasicrystalline. You can see from the diffraction patterns very easily. And if you go to very high cooling rates, what you have is an amorphous matrix in which some aluminum grains are there. You can see the amorphous broad ring with some sharp spots coming from these aluminum. So you have amorphous matrix with those black regions are all aluminum grains. And if you use different cooling rates, one can get different grain sizes. As you increase the cooling rate, the grain size of aluminum keeps on decreasing. You get much bigger grains here, you get much finer grains here. So one can achieve finer and finer grains of aluminum at higher cooling rates. And one can also generate this kind of microstructure which I told you before, that you can have an aluminum inside that kind of nanoparticle of amorphous. How do you get this? As I told you, when the dendrites of aluminum are growing, the liquid is trapped between these dendrites, and when the liquid which is trapped reaches the TG, that liquid undergoes glass transition and you get an amorphous phase. So you can see a nice droplets of amorphous phase in a matrix of aluminum, FCC aluminum one can generate. You can see clearly these are high resolution images, and these lattice fringes, okay, those lines that you are seeing, they are all nothing but atomic planes. Each of those are atomic planes, and inside the amorphous you can't see any of those atomic planes because there are no regular arrangement of atoms in an amorphous phase. So everything is random, so you see a random arrangement of atoms. And one can also take an amorphous plus aluminum kind of sample and then heat it in a DSC and get a quasicrystal, and heat it to still higher temperature, you can get a crystals. And that is what you can see here. Take a sample and can get very fine quasicrystals precipitated in it, and one can get a diffraction pattern. This is called micro diffraction pattern from those particles, and can show yes, you can get a quasicrystal in an aluminum matrix. And one can also find out what are the compositions of these. This is what is called 3-dimensional atom probe studies. I have talked to you earlier about this technique where you can really see atoms, and whatever dots that you are seeing here, each dot represents an atom. Because this is an aluminum iron vanadium alloy, here only iron and vanadium compositional mappings are shown. Because if you show aluminum, aluminum will be 94%, so everything looks black because all these parts will completely fill that volume. So if you look at this and see, there are different domains there. Some regions where the iron is rich, some regions where the iron is poor, again another region where iron is rich. And if you look at this small box and try to enlarge that box and plot what is called compositional profiles as a function of depth, and you can see that there is a small region where this is aluminum, this is vanadium, this is iron. There is a small region where the aluminum is slightly low, and another region where it is aluminum rich. Aluminum rich region is nothing but the alpha aluminum. The low aluminum region is the amorphous region, because you will always get amorphous when there is more amount of alloying elements in it. If you have small amount of alloying element, you will never get amorphous. In order to get an amorphous phase, you have to keep on pumping it with large amount of alloying elements. So usually amorphous phase is that where you have large amount of both iron and vanadium, and alpha aluminum is that where you have more aluminum and small amount of iron and vanadium. And you have an icosidral phase here which has low amount of aluminum but large amount of vanadium here, which has a composition equivalent to Al11V2. This is a phase in this system which is like a Frank-Caspar phase, so its composition is very close to that. And then you have amorphous and again alpha aluminum. So you can see there is a kind of banded type of microstructures where some region of amorphous, some region of quasicrystal, and some region of alpha aluminum, and such a composite, this is all a nano composite because the whole thing is in a small domain. For example, if you look at icosaedral phase, its size it's of the order of around 5 nanometers. So we are talking of such a fine nano composite consisting of amorphous phase and nano quasicrystalline phase and nano aluminum grains, and such a mixture gives you much higher properties, and that is what you see here. You see here the tensile strength, tensile fracture strength as a function of speed of milling. You see at low speeds you get lower strength, basically because you have only aluminum plus quasicrystal here. As you keep on increasing, aluminum grain size is decreasing. If you go to higher and higher velocity, you get a lower grain size, because of which the strength goes up, and if you go to much higher strength, then you get amorphous phase, and once you get amorphous phase, again the strength goes down a little bit. So as long as you have a combination of fine aluminum grains and nano quasicrystalline phase, you get a much higher strength, and that can be shown from the microstructures what we have seen before. One can also study what happens if you vary the composition. What we have seen so far is for one composition 94% aluminum, 4% vanadium and 2% iron. If you vary the composition, you can see the strength reaches a maximum at 4% vanadium. If you fix the iron content and vary the vanadium percentage, you can see when you reach about 4% vanadium, you get the maximum. Similarly, if you fix the vanadium and vary the iron, again you see when you have 2% iron, you get the maximum. So aluminum, 4% vanadium and 2% iron is the best as far as the mechanical properties are concerned, and that is what we have seen before. Whatever microstructures we have seen are all for this particular composition. One can also study different other elements. Vanadium we have seen, we can also study the presence of chromium, presence of manganese. In all the cases at certain particular compositions, one can achieve highest strength, and in all these cases the strength levels are of the order of around 1 gigapascal or even more than that. So one can achieve high strength nano composites in all these alloys. So you have a aluminum plus transition metal, okay, 2 transition metals. If you use only one transition metal, you will not end up in this kind of a microstructure. So at least 2 transition metals are crucial. Okay. So as a summary of this nano composite formation, you can see what kind of combinations give you what kind of microstructures. If you take aluminum, which is kept at the center, and you have lanthanides here, which are nothing but the rare earths, and early transition metals and late transition metals. If you take the aluminum and combine it with the late transition metals, if you have only a binary of these two, you end up in aluminum plus compounds. If you take aluminum plus lanthanides, you get an amorphous phase. Aluminum rare earths, I have shown you various rare earths where glass formation can be obtained. If you take aluminum plus early transition metals, you can get aluminum plus amorphous or aluminum plus quasicrystal, depending on the type of alloying elements that you choose. If you choose manganese, you end up in quasicrystalline phase. If you choose iron or vanadium, you end up in amorphous phases. Like that, if you choose a proper combination of these, you can get that. If you can have a combination of these, aluminum plus early transition plus late transition, you can have a nice combination of amorphous plus quasicrystal plus aluminum. Similarly, if you can have aluminum plus early transition metal plus rare earths, you can have either quasicrystals plus aluminum combinations. Similarly, if you can take aluminum plus late transition metal plus lanthanides. For example, I have shown you the example of aluminum nickel cerium. Aluminum nickel cerium gives you amorphous phase. So like that, one can have examples for all these combinations. We have seen most of these as examples before, and one can generate variety of microstructures, and all of them are basically those which give you high strength and high strengths at high temperatures. That is the advantage of this. So you can see, starting from aluminum, copper, duraluminum, we have made a long journey to all these what are called the exotic alloys. Okay. So we also go to other type of nanocomposites where there are no amorphous phases, no quasicrystals, just simple aluminum plus nano intermetallics. This is one such example. We started talking about it in the last class, aluminum titanium alloys. I told you the aluminum titanium alloys have one important aluminide which is Al3Ti. The advantage of Al3Ti when compared to all other aluminides is because it has large amount of aluminum. It has 75% aluminum, and because of which it has much lower density than any other aluminides, and because it is titanium. For example, nickel aluminides, iron aluminides, titanium aluminides, if you look at it, among all these, which aluminides have the lowest density? Titanium aluminides, obviously, because titanium is low density among nickel, iron and titanium. So titanium aluminides have the lowest density. Among the titanium aluminides, you have three types of aluminides that are possible. I told you, Al3Ti, Alti and Ti3Al. So if you compare these three, Al3Ti definitely has the lowest density because it has highest aluminum amount. So Al3Ti is the best intermetallic as far as the density is concerned among all the aluminides. So if one can produce them in a nanocrystalline form and change the crystal structure from the tetragonal structure to a cubic structure, ordered cubic structure, one can really have a good combination of strength and ductility, and that was one of the objective of making these alloys. And you can see, if you do melt spinning of these alloys, one can generate the in the normal cooling. If you take the alloy and cool it normally, you get aluminum plus DO22 Al3Ti. DO22 is the BCT type of structure, and if you rapidly cool it, you get the L12 structure, and if you take a higher amount of titanium, you get more amount of these L12 structure. And one can add chromium, as I told you before, and as you increase the titanium chromium content, one can produce more and more amount of these L12 phase. And look at these microstructures, you can see fine L12 particles dispersed in a very submicron size of aluminum grains. For example, you can see the grain size of aluminum is of the order of 500 nanometers, that means 0.5 microns. It is very difficult to make this by any conventional route. Even if you do grain refinement of aluminum alloys by inoculation, you will never be able to achieve grain sizes less than about 30 microns or so. So you can see here one can achieve about 0.5 micron grain sizes and get fine particles here of L12 L3Ti. And as I told you, strengths can be retained up to high temperature in these alloys when compared to conventional alloys such as 2017. And we will talk about aluminum iron in the next class. We will stop here.